Hello everyone, my name is Miao Jiao from the University of Auckland. Today I'm going to present a paper titled Two-Attribute Skew-Free, Isolated CP Theorem, and Massively Parallel Joins. This is a joint work with Yufei Tao from the Chinese University of Hong Kong. Join is considered the most important yet expensive operator in relational databases. The schema of the relations can be represented by a hypergraph. For example, in this graph, every vertex represents an attribute and every edge representing the schema of a relation. Three important parameters will be used in the following analysis: the total number of attributes k, the maximum arity alpha, and the total number of tuples in the relations n. The problem of join has been widely studied recently under the massively parallel computation model. In this model, P machines, P is a parameter, are engaged to complete a computation task. The input data is initially distributed evenly on the P machines, and then the computation will be carried out in rounds. In each round, one machine will send out the messages to the other machines and then collect the messages and do some local computation. The objective is to minimize the load, where the load is the maximum number of words received by a machine in the round. So given the hypergraph, which represents a join, we can use the fractional graph theory to derive some important graph theoretic parameters of the join. These parameters are based on optimization computations, which assign for each edge of the hypergraph a non-negative weight, xe. For example, for fractional edge covering number row, it requires to minimize the total weight over all the edges such that for each vertex in the graph, all the incident edges have aggregated weight no less than 1. Similarly, we can define fractional edge packing number tau by changing the minimization to maximization and changing the direction of the inequality. Fractional edge quasi-packing number psi is a little bit different. It is a maximization of the edge packing number over all the induced subgraphs of G. Now we are ready to analyze the existing generic join algorithms that can complete the computation within constant number of rounds. So far, there are only 3 algorithms that fall into this category. Hypercube algorithm proposed by Afridi and Woman, BNHC algorithm proposed by Coutras and Sutsu, and KBS algorithm proposed by Coutras, Beam, and Sutsu for one-round computation. To simplify the analysis, we notice that the load of all the algorithms are following the same pattern, so we define the function fx as n over p to the power of 1 over x, where n is the total number of tuples in the relations, p is the total number of machines in the MPC model. Hypercube algorithm has a load of big O up to a logarithmic factor fq, which is the total number of relations in the query. BNHC is related to the number of attributes in the query, k. KBS is related to the quasi-packing number. Although these 3 algorithms have different load, it is worth noting that all these algorithms are worst-case optimal in the sense that you won't be able to come up with a generic join algorithm whose load is small o f to the number of relations, to the number of attributes, and quasi-packing number. So in this sense, all the 3 algorithms are worst-case optimal. Specifically, for hypercube algorithm, it is worst-case optimal on the Cartesian products. A BNHC algorithm is optimal on Cartesian products as well, where each relation in the join will have only one attribute. The KBS algorithm is optimal on certain type of joins, for example, the line join. A apart from the generic join algorithm we discussed here, there are a large number of joins on specific join. For example, the acyclic join, Loomis-Whitney join. So in this paper, we focus on the generic join algorithms. In terms of a lower bound, it's a little bit of a blur here. The lower bound of F row applies to all the joins, but it's not necessarily tight. Example raised by Hu Xiao this year shows that there are cases where F tau is actually tight lower bound as opposed to F row. These cases are called degree 2 joins, where each attribute belongs to exactly two relations. For one round computation algorithms, join algorithms with only one round computation, the lower bound can be F psi. But the relation of the three parameters is still unclear. For example, psi is or no less than tau and rho. However, the relationship between tau and rho is unclear, and it is still unclear whether there is a third parameter that can better capture the lower bound. So it is an open problem for us to design a generic algorithm that can meet the lower bound as much as possible. Along this direction, we have done some explorations and have achieved very interesting results. We have proposed in this paper a new generic join algorithm whose load can be bounded by a newly identified graph theoretical number phi. We call it generalized vertex packing number. So this generalized vertex packing number is strongly related to the existing graph theoretic number, and it has some very nice properties. For example, when the maximum arity alpha equals to 2, it can be proved that phi equals to rho. And we can bound our generic join algorithm's load by f alpha phi over 2. So when alpha equals to 2, we cancel these two factors, and phi equals to rho, which leads to a directly optimal solution on binary joins meeting the lower bound of f rho. It's just one side of the coin. On the other side, we can meet the lower bound of f tau on a type of join called bow join, where we have even number of attributes a1 to ak over 2, b1 to bk over 2, where we have one relation for a attributes, one relation for b attributes, and for each ai and bi, we have a relation with two attributes. On this type of join, we can guarantee that our load can be bounded by f tau, where tau is the fractional packing number. So this is quite interesting in observing that with one generic join algorithm, we actually can meet both the lower bound of f rho and the lower bound of f tau in different scenarios. For specific type of join, for example, alpha uniform join, where each relation has alpha attributes, we can refine our analysis to get a tighter bound. For a specific type of join called K-choose alpha join, where we have a relation for every combination of alpha attributes out of K attributes, we can outperform KBS strictly when alpha is greater than 2 and smaller than K. In symmetric join, in which it is an alpha uniform join and each attribute participates in the same number of relations, we can further refine the bound. This is the overview of the results we have in the paper. Now let's look at the definition of the generalized vertex packing number. We start with fractional edge covering number rho, and then find its dual problem, fractional vertex packing number. So now we're going to remove the non-negative constraint of the fractional vertex packing number and then get the generalized vertex packing number by allowing the variable to take negative values. This phi is related to a fractional weighted edge packing number phi bar. We say it's weighted because here the constraint is the same as the fractional edge packing number, but the objective function has a multiplication factor in each edge weight. So note that if the join is binary join, then phi bar will be equal to tau, which is fractional edge packing number. For all the cases, we can prove that phi bar equals to b minus phi. So this invariant is helpful for us to establish our isolated CP theorem. Now I have time to briefly introduce the two techniques of the paper. The motivation of the two attribute skew free is we would like to relax the strong requirements of skew free in bin HC so that there will be space for us to push the boundary of the load. So in bin HC, it requires all the subsets of attributes of different sizes to be skew-free. This is too tight and hard to be satisfied if we want to kind of move the load a little bit lower. In this sense, we decided to relax this condition and focusing on single attributes and attribute pairs. The skew-free will only apply to the subset of size no more than 2. After that, we are going to decide the value of those skewed attributes and then to evaluate the residue query. The main challenge of evaluating this residue query is that the Cartesian product of these isolated attributes can be extremely high. So in order to bound them, we have used a very interesting and novel proof. So this proof actually starts with a newly introduced the parameter phi bar, and we use the edge assignment of the phi bar of different edges and progressively upgraded to rho, which is fractional vertex cover and which is upper bound. And during the process, we guarantee that the size of a Cartesian product is not changed. So in this sense, we bounded the size of a Cartesian product with phi bar, and phi bar is related to phi, and then we connect the load with phi. So that is a part I would like to explain in this short time. Thank you very much.